The data refreshed at 3:47 UTC, and when I saw the new orbital parameters, I sat very still in the dark and realized that 3I Atlas had altered its trajectory for the third time in 18 months. And this time, the projected path intersects the plane of Earth's orbit. Welcome to Sleepy Cosmos, where we explore the quiet truths hidden between the stars. Subscribe for more stories the universe wasn't ready to tell. I've been tracking 3I Atlas since the night it was first flagged as an anomaly. Not the night the public heard about it, the night it appeared in the pre-release data streams, before anyone had decided what to call it, before the naming committees and press releases and carefully worded academic papers. That was January 14th, 2024, at the Haleakala Observatory on Maui, where the Atlas Survey Telescope caught something moving against the background stars in a way that didn't match any known trajectory in our solar system's catalog of predictable motions. I remember the email subject line, "Possible hyperbolic interloper needs confirmation." The language was clinical, almost dismissive, but I could feel the uncertainty beneath those words, the way you can hear someone's heartbeat change over the phone even when their voice stays steady. Because hyperbolic meant it wasn't bound by our sun's gravity, and interloper meant it came from somewhere else, somewhere between the stars, where nothing should be moving with purpose, where everything should be dead and cold and following the mathematics of ballistic drift. 3I Atlas wasn't supposed to be interesting. It was supposed to be another Oumuamua, another Borisov, a chunk of interstellar debris tumbling through our neighborhood on its way to somewhere else, briefly illuminated by our sun before vanishing back into the dark. We'd log it, measure it, write papers about its composition and velocity, and then forget it as it receded beyond the orbit of Neptune and became just another faint smudge in the archive images. But 3I Atlas didn't do what it was supposed to do. It changed direction. Not dramatically nothing Hollywood would notice. No sudden right angles or impossible accelerations. Just a subtle deviation in its path, a gentle curve that appeared in the data over the course of several weeks, like watching a river slowly change its course. At first, everyone assumed it was outgassing the standard explanation when comets or icy bodies behave unexpectedly. When sunlight heats volatile materials beneath the surface, they sublimate and jet out into space, creating tiny rocket engines that can nudge an object off its predicted trajectory. We see this all the time with comets. It's normal. It's physics. But 3I Atlas wasn't outgassing. There were no jets, no visible coma, no spectroscopic signatures of water vapor or carbon dioxide or any of the usual suspects. The Hubble Space Telescope looked. The James Webb Space Telescope looked. The European Southern Observatory's Very Large Telescope looked with instruments sensitive enough to detect the faint glow of organic molecules evaporating in hard vacuum. Nothing. 3I Atlas was changing course without any visible mechanism for doing so. That was the first time I felt the wrongness settle into my chest like cold water. Not fear, exactly, more like the sensation of standing at the edge of a cliff you didn't know was there. That moment when your inner ear tells you something fundamental about your position in space has changed. Let me take you back to the beginning, to the discovery itself, because context matters when you're trying to understand something that doesn't fit any existing framework. The Atlas system, the Asteroid Terrestrial Impact Last Alert System, wasn't designed to find interstellar objects. It was built to spot asteroids that might pose a threat to Earth, scanning the entire visible sky every few nights, looking for anything that moves. It's an early warning system, a cosmic smoke detector, and it works by comparing images of the same patch of sky taken at different times. If something appears in one image that wasn't there before, or if something that was there has moved, the software flags it for human review. On that January night, Atlas flagged an object in the constellation Ursa Major with a preliminary velocity that made no sense for anything gravitationally bound to our solar system. The numbers suggested it was moving at roughly 87 kilometers per second relative to the sun, fast enough that solar gravity alone couldn't explain its trajectory. fast enough that it had to have originated beyond the heliosphere, beyond the Kuiper belt, beyond the scattered disk where the last gravitational echoes of our sun's formation still linger. The Discovery team ran the standard checks. They looked for parallax error, instrument calibration issues, software glitches, all the mundane explanations that usually turn exotic candidates into data artifacts. But the object remained consistent across multiple observation nights, across different telescopes, across different observation teams using different equipment and different analysis pipelines. Within a week, they had enough positional data to calculate a preliminary orbit. The eccentricity came back as 1.7, meaning this object was on a hyperbolic trajectory, unbound from the sun, passing through our solar system like a stone thrown through a window. Interstellar. Definitely interstellar. They designated it 3I Atlas, the third recognized interstellar object after Oumuamua and Borisov. The initial excitement in the astronomical community was palpable. Every interstellar object is precious because they're so rare we might get one every few years, if we're lucky. And each one is a sample of material from another star system, another planetary formation process, another corner of the galaxy that evolved completely independently from our own. They're time capsules and comparative data points and messengers from places we'll never reach. The early observations painted a picture of something strange but not unprecedented. Spectroscopic analysis suggested a composition heavy in carbon compounds, tholins, perhaps, those complex organic molecules created by irradiation of simpler compounds in the cold of deep space. The object showed no signs of cometary activity despite passing within 2.1 AU of the Sun closer than Mars, far enough to heat most icy bodies to the point of visible outgassing. Its light curve, the pattern of brightness variation as it rotated, was complex and irregular, suggesting either a highly elongated shape or a surface covered in regions of drastically different reflectivity. The rotation period appeared to be roughly 17.3 hours, though the signal was messy, complicated by what looked like periodic flares or brightness spikes that didn't match any standard tumbling pattern. Size estimates were fuzzy, as they always are with objects we can't resolve spatially. Based on its brightness and assumed albedo, astronomers calculated it was somewhere between 600 and 900 meters in diameter, roughly twice the length of the Empire State Building, if it was spherical. If it was elongated like Oumuamua, it could be even larger, perhaps a kilometer or more along its longest axis. And then, in March of 2024, 3 months after discovery, the first deviation appeared. I was running orbit updates through JPL's Horizons system when I noticed it. Horizons is the gold standard for solar system ephemerides if you want to know where something will be at any given time. You query Horizons, and it gives you positions accurate to within meters based on the best available orbital data. It's the system NASA uses for mission planning, the system professional astronomers use for pointing their telescopes, the system that predicts eclipses and satellite transits and asteroid close approaches with unnerving precision. When I queried 3I Atlas's position for a date 2 weeks in the future, the predicted position was off from where I'd calculated it should be based on the previous month's data. Not by much, just a few arc-seconds on the sky. But in astronomy, especially when tracking objects with well-constrained orbits, a few arc-seconds is enormous. It's the difference between knowing where something is and having to search for it. I assumed I'd made a mistake. I reran my calculations, checked my reference frame conversions, verified my epoch dates. The discrepancy remained. Then I checked the orbit solution update history, and I saw that JPL had pushed a revised orbit based on new observations that showed 3I Atlas was not following its predicted path. The object had accelerated, or more precisely, it had experienced a non-gravitational acceleration along a vector that didn't align with sunward pressure. In the technical notes, the dynamics team had flagged it as possible outgassing event, low confidence, awaiting additional photometric data. I pulled up the light curves from that period. No change in brightness, no cometary coma, no spectroscopic evidence of volatile loss. Just a clean, consistent dimming as the object moved away from the sun, exactly as you'd expect from a dark, inert body obeying the inverse square law of illumination. But its path had changed. The deviation was small enough that most of the community treated it as a minor oddity, an observational artifact that would resolve itself with more data. Interstellar objects are difficult to track with precision because they move so fast and they're so faint. By the time you've collected enough observations to nail down their orbit, they're already receding into the outer solar system, where only the largest telescopes can follow them. Orbital uncertainties are normal. Small corrections are normal. Except this wasn't a correction. This was a real, physical change in trajectory that required energy from somewhere. I started watching 3I Atlas more carefully after that. Not obsessively. I had other work, other projects, a life that existed outside of this one enigmatic object, but it had hooked something in me. That first deviation. Because if an interstellar object can change course once without a visible mechanism, what's to stop it from doing it again? The second deviation came in August 2024, and this one was harder to dismiss. By then, 3I Atlas had crossed the orbit of Mars and was outbound, heading toward the asteroid belt with a velocity that would carry it past Jupiter's orbital distance by early 2025. It should have been getting fainter, colder, more predictable as it moved away from the sun's heating influence. Instead, at approximately 3.7 AU from the sun, about the same distance as the outer edge of the asteroid belt, it made another subtle course correction. This time, the acceleration was larger and better documented. Multiple observatories caught it in the act of deviating, and the tracking data was clean enough that there was no ambiguity about what was happening. The object had experienced another non-gravitational acceleration, this one lasting approximately 6 days, that changed its velocity by roughly 0.3 meters per second. That might not sound like much, but in orbital mechanics, every meter per second matters. Over time, small velocity changes accumulate into large positional differences. This particular acceleration was enough to shift 3I Atlas's trajectory by several thousand kilometers over the following months. And again, there was no outgassing, no jets, no coma, no change in its light curve or spectrum, just a clean, directed acceleration that looked for all the world like someone had fired a thruster. The academic papers started appearing in preprint servers within weeks. Non-gravitational acceleration of interstellar object 3I Atlas, implications for composition and structure, radiation pressure modeling of high albedo interstellar interlopers, asymmetric sublimation scenarios for dark, carbonaceous interstellar objects. Every paper had the same underlying structure. Acknowledge the anomaly, propose a natural mechanism, conclude that more observations are needed. They were careful, measured, professional. They did what scientists are supposed to do. They looked for the simplest explanation that fit the data without invoking exotic physics or abandoning the frameworks that have served us well for centuries. But I could read between the lines. I could see the uncertainty, the reaching, the way each proposed mechanism required special conditions or unusual geometries or convenient alignments of unobservable properties. The explanations worked, technically, but they felt forced, like trying to fit a square peg through a round hole by shaving off just enough corners that it technically slides through. I printed one of the papers and pinned it above my desk, not because I believed it, but because I wanted to remember the exact moment when the scientific community decided this was still a normal thing that required normal explanations. On the printed page, I highlighted a single sentence from the conclusion. While the observed non-gravitational accelerations remain difficult to explain within standard cometary outgassing frameworks, we emphasize that natural mechanisms have not been exhausted. Natural mechanisms have not been exhausted. That phrase kept me awake some nights. Because there's a corollary that nobody writes in peer-reviewed papers. If natural mechanisms are exhausted, then what? I should tell you about the sound. because that's when things started feeling different for me, not just intellectually puzzling, but viscerally wrong. In September 2024, the Deep Space Network picked up something odd from the direction of 3I Atlas. I say picked up. Loosely, the DSN isn't designed to listen for signals from random solar system objects, and it certainly wasn't pointed at 3I Atlas for any official purpose. But one of the arrays was conducting a routine calibration exercise, scanning across a section of sky to measure background noise levels when it swept past the object's position, and the noise level changed. It wasn't a signal, not in the traditional sense. No modulation, no information content, no carrier wave or data structure. Just a slight elevation in radio brightness at certain frequencies, specifically in the 1.4 GHz band, the so-called water hole, where hydrogen and hydroxyl emission lines bracket one of the quietest regions of the radio spectrum. It's where SETI researchers traditionally listen for potential artificial signals because natural noise is minimal there. The elevation was small, barely above the noise floor, and it only lasted for the few minutes that the array was pointed in that direction. When they tried to replicate the observation a week later, there was nothing unusual, just the expected thermal emission you'd get from any dark body at that distance, and temperature. The DSN team documented it in their internal logs and moved on. Probably interference from a satellite, they noted. Possibly instrumental artifact. Not significant. But I got a copy of the raw data through a friend who works antenna calibration, and I listened to it, not the processed, filtered version. The raw feed, converted to audio frequencies, fed through headphones in a quiet room at 3 in the morning. Static, mostly. The hiss and crackle of radio noise, the background whisper of the universe, and underneath it, for just a few seconds, something that might have been a pattern. Not regular enough to be artificial, but not quite random enough to be natural. A rhythm that almost assembled itself and then dissolved back into noise before you could be sure it was ever there. I played it 17 times that night, listening with my eyes closed, trying to decide if I was hearing something real or if I was pattern-matching silence into meaning because I wanted there to be meaning. I still don't know, but I saved the file, and sometimes, late at night when I'm reviewing data, I play it again, just to remind myself that uncertainty has a sound, and it sounds like static that might be trying to become music. The thing about tracking an interstellar object is that it requires patience bordering on meditation. You can't watch it in real time like you might watch Mars move against the stars over weeks. These objects move so quickly that they cross the entire sky in months, and they're so faint that you need large telescopes with long exposure times to see them at all. Each observation is a single point of light, captured over minutes or hours, a position and brightness measurement that tells you where the object was at a specific moment, but nothing about where it's going or what it's doing. To understand the trajectory, you need many observations spread over time, and then you need to fit those observations to a mathematical model of orbital motion. It's like trying to understand the shape of a coastline by taking GPS measurements from a speedboat every few miles. You can do it, but you need enough data points and enough time to let the pattern emerge. So I collected data points. I queued observations when I could get telescope time. I scraped public databases for photometry from other observers. I built spreadsheets and plots and orbital integration models, feeding them data from the Minor Planet Center and JPL and the European Space Agency's Near-Earth Object Coordination Center. Most nights, the data showed exactly what you'd expect. 3I Atlas, following its modified trajectory outbound from the sun, growing fainter as it receded, rotating serenely through empty space. The light curve continued its complex variation, that irregular brightness pattern that suggested either a lumpy, asymmetric body or a surface with variable reflectivity. The spectrum remained dark and red, consistent with organic rich material that had been irradiated and processed by cosmic rays over millions or billions of years of travel between stars. It looked in most respects like exactly what it was supposed to be, an interstellar asteroid following the laws of physics through our solar system. But every few weeks, I'd run an orbit update and find that the predictions had drifted again. Not always in the same direction, not always with the same magnitude, but consistently, persistently, the object was not quite where the gravitational models said it should be. Small corrections, tiny accelerations, deviations that sat right at the edge of observational uncertainty, where you couldn't quite prove they were real, but you couldn't quite dismiss them either. It felt like watching someone breathe in the dark. You can't see the motion directly, but you can see the blanket rise and fall, and you know something is there, moving, alive. By December 2024, 3I Atlas had reached approximately 4.2 AU from the Sun beyond the orbit of Mars, deep in the asteroid belt, far enough from Earth that it required serious telescope aperture to track. The object was magnitude 22, invisible to all but the largest observatories, and getting fainter every week as it receded. The general consensus in the astronomical community was that the story was essentially over. 3I Atlas would continue outbound until it passed beyond Neptune's orbit sometime in 2026, at which point it would fade below the detection threshold of even Hubble and Webb and become just another statistical entry in the catalog of interstellar visitors. Interesting for what it had shown us about non-gravitational forces and possibly exotic composition, but ultimately another data point in a category of objects we were just beginning to understand. Papers were being written, careers were being advanced, conference presentations were being prepared. The narrative was settling into place. 3I Atlas, the third interstellar object, showed unusual but explicable behavior consistent with complex outgassing patterns from a volatile poor body, and represents an important case study for future observations of similar objects. I wanted to believe that narrative. I wanted to file my observations, write my section of the summary paper, and move on to other projects. I had a tenure review coming up. I had students who needed advising. I had a life that existed beyond this one strange rock from between the stars. But then, on December 17th at 3:47 UTC, while most of the northern hemisphere was sleeping and the observatory was running an automated sequence I'd programmed 3 days earlier, the data refreshed with new orbital parameters from JPL, and I saw that 3I Atlas had changed course again. This time, it wasn't a small correction or a subtle deviation that could be explained away as observational uncertainty. This was a major trajectory alteration, a course change that had occurred over a period of approximately 2 weeks in late November and early December, during which time the object had been poorly observed due to its proximity on the sky, to bright stars and the sun's position relative to major observatories. The acceleration had been sustained and directed, changing the object's velocity by nearly 3 meters per second, and the new trajectory. I sat very still in the dark control room, lit only by monitor glow and the faint red safety lights that preserved night vision, and I read the orbital elements 3 times to make sure I was understanding them correctly. The new trajectory was no longer carrying 3I Atlas out of the solar system on a clean hyperbolic escape path. It was curving back inward. Let me give you the numbers, because numbers are the only things I can trust when everything else starts feeling uncertain. The revised orbit solution showed that 3I Atlas's perihelion, its closest approach to the Sun, had changed from 2.1 AU, which it had already passed in March 2024, to a new, future perihelion of approximately 1.8 AU, projected to occur in August 2025. The object wasn't leaving. It was coming back around for another pass, closer this time, following a trajectory that looked less like a hyperbola and more like a highly eccentric, comet-like orbit. Except no interstellar object should be able to do that. By definition, interstellar objects are on hyperbolic or parabolic trajectories because they arrived with excess velocity that our sun's gravity can't capture. They're shooting through, not orbiting. The only way to change a hyperbolic trajectory into an elliptical one is to lose a significant amount of velocity, either by aerodynamic drag in a thick atmosphere which doesn't exist in deep space, or by some propulsive mechanism that provides continuous thrust in exactly the right direction. I pulled up the acceleration vectors that the JPL dynamics team had calculated from the tracking data. The acceleration wasn't random or chaotic. It wasn't the kind of patchy, asymmetric force you'd get from irregular outgassing. It was smooth, sustained, and directed almost perfectly along the object's velocity vector, a braking maneuver, in other words. As if something was deliberately slowing it down. I ran the numbers through my own orbit integration software to verify JPL's solution. I used different gravitational models, different integration methods, different starting epochs. Every simulation came back with the same result. 3. I-Atlas was no longer leaving the solar system. It had modified its trajectory enough that it was now marginally bound to the Sun, with an orbital period of approximately 14.7 years, and an aphelion, its farthest point from the Sun, somewhere beyond Neptune's orbit. It had captured itself. Or something had captured it, or it had chosen to stay. I need you to understand the energy budget involved in this kind of maneuver, because the numbers are what keep me anchored when my thoughts start spiraling into territory that feels more like science fiction than science. To change 3 I-Atlas's velocity by 3 meters per second, you need to impart momentum. The amount of momentum depends on the object's mass, which we can estimate from its size and assumed density. If we take the conservative estimate of 600 meters diameter and assume a density similar to other carbonaceous asteroids around 1,300 kilograms per cubic meter, we get a mass of roughly 150 million kilograms. To accelerate 150 million kilograms by 3 meters per second requires 450 million kilogram meters per second of momentum transfer, which translates to approximately 675 megajoules of kinetic energy. 675 megajoules is equivalent to the explosive energy of about 160 kilograms of TNT. It's not a huge amount of energy on a cosmic scale. It's less than the kinetic energy of a typical small asteroid impact, less than the thermal energy released by a moderate solar flare. But it's a lot of energy to impart to an object through natural processes when that object is far from the Sun, cold, and showing no signs of active outgassing. If you wanted to produce that kind of acceleration through cometary jets, you'd need to eject roughly 10,000 kilograms of material at typical outgassing velocities of around 500 meters per second. 10 metric tons of ice or dust, sublimated and ejected in exactly the right direction over exactly the right time period. And you'd be able to see it. You'd see the jets. You'd see the coma. You'd detect the spectroscopic signatures of water vapor or carbon dioxide or whatever was doing the outgassing. The object would brighten as sunlight scattered off the ejected particles. It would leave a faint tail pointing away from the Sun. None of those things happened. 3. I-Atlas remained dark, quiet, and spectroscopically inert while it changed its velocity by 3 meters per second and altered its fate from interstellar wanderer to semi-permanent solar system resident. I wrote up these numbers in a brief technical note and submitted it to the Minor Planet mailing list, a semi-private forum where professional astronomers discuss ongoing observations of asteroids and comets. I kept the tone neutral, the conclusions minimal. Significant non-gravitational acceleration observed. Natural mechanism unclear. Further photometric and spectroscopic observations strongly encouraged. The responses started arriving within hours. Most were variations of the same theme. Interesting observation. Probably explained by delayed sublimation of buried volatiles. Need more data to constrain composition. Thanks for sharing. Professional courtesy wrapped around professional skepticism. But a few responses were different. A few observers said they'd noticed the same thing and had been quietly wondering about it. One researcher at ESA sent me a private message. I've been tracking the light curve changes during the acceleration period. There's a pattern I can't explain. Can we talk offline? We set up an encrypted voice call for the following evening. She wanted encryption, she said. Not because we were discussing anything classified or proprietary, but because she didn't want her preliminary thoughts ending up on social media or in a sensationalized news article before she'd had time to verify them properly. I understood completely. Her name was Dr. Elena Vasquez, and she worked in ESA's Space Situational Awareness program, tracking objects that might pose a risk to satellites or spacecraft. She'd been following 3I Atlas since discovery because interstellar objects, while not a collision risk to Earth on their initial pass, represented an unknown factor in her models. If an object could change course unpredictably, then maybe it needed to be monitored more carefully than the standard gravitationally bound asteroids that followed predictable paths. I've been running high-cadence photometry whenever I can get telescope time, she told me, her voice slightly distorted by the encryption software, but still carrying an undercurrent of something I recognized, the specific flavor of unease that comes from seeing data that shouldn't exist. Catching it every few hours during the acceleration period in November and December, and the light curve, it's not behaving like a tumbling body should. She sent me her data files, and I loaded them into my analysis software while we talked. What I saw made my mouth go dry. The light curve of a rotating asteroid or comet is usually periodic. The object spins, different faces catch sunlight at different angles, and the brightness varies in a repeating pattern. Sometimes it's simple, just one peak and one valley per rotation, if the object is elongated and tumbling end over end. Sometimes it's more complex if the rotation is chaotic or if there are multiple distinct surfaces with different reflectivity. But it's always chaotic in the mathematical sense, deterministic but unpredictable in detail, the kind of complex variation that arises from rigid body dynamics and gravitational torques, and whatever collisions shaped the object eons ago. Elena's light curve showed something different. During the acceleration period, the brightness variations were still there, still showing that roughly 17-hour period that had been consistent since discovery. But superimposed on top of the rotation signal was something else. Periodic brightness spikes, occurring roughly every 41 hours, that didn't match the rotation period at all. It's like there's something on the surface that activates periodically, Elena said, not tied to the object's rotation, not tied to its distance from the sun, not tied to anything obvious in its orbital geometry, just periodic activation. Every 41 hours, something causes a brief increase in brightness about 0.3 magnitudes, lasting for approximately 2 hours, then fading back to baseline. I stared at the data plot, watching the pattern repeat itself over weeks of observations. She was right. The spikes were regular, consistent, occurring with clockwork precision, even as the underlying rotation signal varied slightly due to what was probably precession or nutation, the complex wobbling that affects most rotating bodies. "Have you checked for instrumental artifacts?" I asked, already knowing she had. Different telescopes, different cameras, different analysis pipelines. The signal is real. Whatever's causing those brightness spikes is physically happening on or near the object. "Specular reflections," I suggested, grasping for natural explanations. Maybe there's a highly reflective patch on the surface, and the 41-hour period is some beat frequency between the rotation and... "And what?" Elena interrupted gently. "The orbital motion? The nutation period? I've run the calculations. There's no natural beat frequency that produces a 41-hour period given the object's known rotation rate and orbital parameters." We sat in silence for a moment, the encrypted connection humming faintly in the background. "It's like something is turning on and off," she finally said. "That's what it looks like. I know that sounds insane. I know that's not how asteroids work, but that's what the data shows." I spent the next 3 days barely sleeping, running every analysis I could think of on Elena's photometry data and cross-referencing it with my own observations and everything available in the public databases. The pattern held every 41 hours. During the acceleration period in November and December 2024, 3I Atlas had brightened by about 0.3 magnitudes for approximately 2 hours before fading back to its baseline brightness. The spikes were real, consistent across different observers and different instruments. And then, in mid-December, right around the time the acceleration stopped and the object settled into its new trajectory, the brightness spikes stopped too. 3I Atlas went back to showing just its normal rotation signature, complex and irregular, but no longer punctuated by those mysterious periodic flares. Whatever had been happening was no longer happening. The object had changed course, and then it had gone quiet. I made coffee at 4 in the morning and stood by my window, looking up at stars I couldn't quite see through the city's light pollution, and I tried to think of any natural process that could produce that pattern. Solar reflection from a highly inclined flat surface? Possible, but the timing was wrong and the geometry didn't work out. Outgassing jets rotating into view? Possible, but there was no spectroscopic evidence of outgassing and the period didn't match the rotation. Impact events kicking up dust? Possible, but 3I Atlas was in empty interplanetary space with no nearby bodies to impact it, and impacts don't happen with metronomic regularity. Tidal heating from some unknown internal process? Possible, but tidal heating requires a gravitational gradient, and 3I Atlas was too far from any massive body to experience significant tidal forces. I kept coming back to the same uncomfortable conclusion. The brightness spikes looked less like natural phenomena and more like something being deliberately activated, and the 41-hour period looked less like a natural frequency and more like a schedule. I didn't write that in my notes. I didn't say it out loud, but I thought it, and thinking it changed something fundamental about how I looked at the data from that point forward. January 2025 was unusually clear at the observatory. High-pressure systems parked over the mountain for weeks at a time, giving us night after night of stable seeing and dark skies. I used the time to collect as much data on 3I Atlas as I could, even though it was now faint enough that each observation required hours of integration time to get a decent signal-to-noise ratio. The object was at 4.5 AU now, roughly the distance of Jupiter's orbit, though Jupiter itself was on the opposite side of the Sun. 3I Atlas was alone in a relatively empty region of space, following its new trajectory inward at a leisurely 18 kilometers per second, still invisible to anything but professional telescopes. I tracked its position night after night, updating my orbital models, looking for any sign that the acceleration might resume. The trajectory remained stable, following gravitational physics with no detectable deviations. It was as if the object had finished whatever it was doing and was now content to coast. But I noticed something else in those January observations. The rotation period was changing. Not dramatically, just a few minutes over the course of several weeks, but measurably slowing down. From 17.3 hours in early December to 17.8 hours by late January. That's unusual, but not unprecedented. Asteroid rotation rates can change over time due to the Europy effect, where an isotropic thermal emission from a spinning body creates tiny torques that gradually speed up or slow down the rotation over years or decades. Except the Yorp effect is slow, evolutionary. You don't see measurable changes over weeks. You see them over years or centuries as the object absorbs sunlight on one side and radiates heat on the other, and those tiny imbalances gradually change the rotation state. 3I Atlas was changing its rotation rate much faster than Yorp could explain, as if something inside it was redistributing mass, or as if external forces were acting on it in ways that affected its angular momentum. I documented the rotation period change in my observing logs, added it to the growing list of things that didn't quite make sense, and kept watching. And then, on February 3rd, 2025, something happened that made every other anomaly seem small by comparison. It was a routine observation, part of a long-term monitoring program I'd set up to track 3I Atlas through its new orbit. The telescope was running robotically, following a pre-programmed sequence. Image the target field, measure the sky background, Calculate the object's brightness and position. Move to the next observation. I wasn't even at the observatory. I was home, asleep, while the telescope did its work under the clear winter sky. The anomaly showed up in the automated processing pipeline at 6:14 UTC. The software flagged it as a possible satellite trail or cosmic ray hit a bright streak across one of the images that didn't match the expected point source signature of a distant asteroid. When I checked the images the next morning, I saw that it wasn't a satellite trail or a cosmic ray. 3I Atlas had flared. Not the gentle 0.3 magnitude brightness spikes Elena had seen during the acceleration period. This was a major flare, a sudden brightening by nearly 4 magnitudes that lasted for approximately 18 minutes before fading back to normal. In that 18-minute window, the object had briefly become bright enough to be visible in amateur telescopes, had anyone known where to look. 4 magnitudes is a brightness increase by a factor of about 40. For 18 minutes, 3I Atlas had released as much light as a 40-meter diameter asteroid with high albedo at the same distance would reflect continuously. And then it had stopped, as abruptly as it had started, and gone back to being a faint, dark speck. I checked the timing, 6:14 UTC on February 3rd. I counted backward in 41-hour increments from the last observed brightness spike in mid-December. The flare had occurred exactly on schedule. After 6 weeks of silence, whatever had been causing those periodic brightness spikes had activated again. Once, briefly, and then it had gone quiet once more. I immediately sent messages to Elena and to every other observer I knew who had been tracking the object. Had anyone else seen it? Had anyone captured spectroscopy during the flare? Had anyone been lucky enough to have their telescope pointed at exactly the right patch of sky at exactly the right moment to catch 18 minutes of anomalous behavior from an object 4.5 AU away? The responses trickled in over the following days. One observatory in Chile had caught the tail end of the flare before sunrise ended their observing window. One amateur astronomer with a large backyard telescope had accidentally captured it while imaging a nearby galaxy and hadn't realized what he'd recorded until I told him to check his timestamps. Nobody had spectroscopy. Nobody had been set up to catch rapid photometry with sub-minute cadence. All we had were a handful of images showing a faint object that was briefly much brighter than it should have been. The Chilean observatory sent me their data, and I spent an evening analyzing the flare decay. The fade back to baseline brightness wasn't instantaneous. It took about 3 minutes for the object to return to normal brightness after the peak, following a roughly exponential decay curve. That decay timescale is important. It's too fast for most thermal processes. If you heat up a rock, it cools slowly, radiating its heat over hours or days, not minutes. But it's consistent with the timescale you'd see if a highly reflective surface was rotating out of view, or if something luminous was being shut off. I plotted the decay curve on a log scale and stared at it until my eyes watered, looking for any hint of physical process that could produce that specific timescale. I found nothing convincing. The professional astronomy community's response to the February flare was interesting in what it revealed about the sociology of science. Most researchers acknowledged that something unusual had happened, but there was a clear reluctance to engage with just how unusual it was. Papers started appearing with titles like Transient Optical Brightening of Interstellar Object, 3I Atlas Impact Event, or Cryovolcanism. They proposed mechanisms, a small impact from an unseen meteoroid that had briefly heated the surface, triggering localized sublimation of buried volatiles, or cryovolcanic activity from exotic ices in the interior reaching critical pressure and venting suddenly, or rotational disruption from spin-up, though that didn't explain the rapid decay. Each mechanism was possible in isolation. Each had precedent in solar system science. But none of them explained why the flare occurred exactly on schedule with the previous 41-hour periodic spikes, and none of them explained why it happened once and then stopped. The pattern was becoming clearer, at least to me. 3I Atlas did things in bursts of activity separated by long periods of quiescence. It accelerated for several weeks, then stopped. It flared periodically during the acceleration, then went silent. It produced one final flare 6 weeks later, then went silent again. It felt less like natural processes and more like something operating according to a plan, completing tasks, then waiting. I didn't say this in public forums. I didn't write it in papers. But I started a private document on my encrypted drive, titled only with the date, where I wrote down everything I was thinking without the careful hedging in diplomatic language required for professional communication. In that document I wrote, Hypothesis 3. Atlas is not a natural object. Or it contains something that is not natural. The pattern of activity suggests deliberate behavior, course correction followed by confirmation signal. The 41-hour period may be communicative, a beacon. The trajectory change is too precise and too purposeful to be coincidental. And then I wrote, but why would an interstellar probe, if that's what this is, change course to stay in our solar system? Why slow down? Why announce itself with flares and then go quiet? What is it waiting for? I saved the document and closed it, and didn't open it again for 3 weeks, because acknowledging those questions felt like crossing a line from science into speculation, and I wasn't ready to take that step publicly. But privately, alone at my desk, with the curtains drawn and the office door locked, I was already across that line. I had been since December, when I first saw the new trajectory data. In March 2025, the conversation changed. Not in astronomy circles there. The discussion continued in its careful, measured way, accumulating observations and proposing mechanisms and waiting for enough data to make definitive conclusions. But in other circles, less bound by peer review and academic caution, people started asking different questions. An article appeared in a popular science magazine. Is 3I Atlas an interstellar probe? What the data really shows? It was well researched. Interviewed several professional astronomers, not me, I declined to comment, and laid out the sequence of anomalies in plain language accessible to non-specialists. The article didn't claim 3I Atlas was artificial. It carefully presented the natural explanations alongside the observations and let readers draw their own conclusions. But by putting all the anomalies together in one place, the course changes, the brightness spikes, the flare, the perfect timing, it created a narrative that was hard to ignore. The internet did what the internet does. Within days, 3I Atlas was trending on social media, spawning YouTube videos and Reddit threads and podcast discussions. Most were sensationalized, some were thoughtful, a few were genuinely insightful. The speculation ranged from reasonable to absurd. Alien probe, post-biological von Neumann machine, remnant of an ancient civilization, secret government spacecraft, elaborate hoax. I watched the discourse spiral with mixed feelings. On one hand, the attention meant more resources might be directed toward observing the object, more telescopes might be pointed its way, more data might be collected. On the other hand, the signal-to-noise ratio of public discussion was abysmal, and sorting genuine insights from conspiracy theories and wishful thinking was exhausting. The professional community's response was predictable, a collective circling of the wagons, emphasizing the importance of evidence-based reasoning and warning against premature conclusions. Press releases from NASA and ESA carefully explained that while 3I Atlas showed interesting behavior, there was no credible evidence for artificial origin, and natural mechanisms remained the most parsimonious explanation. Which was true, technically. Natural mechanisms did remain the most parsimonious explanation if you took each anomaly in isolation. It was only when you looked at the pattern, the sequence, the timing, that the natural explanations started to feel inadequate. But science doesn't work on patterns and feelings. It works on evidence and models and falsifiable hypotheses. And we didn't have enough evidence to falsify the null hypothesis that 3I Atlas was just a weird rock with unusual properties. So we waited, and we watched, and we collected more data. By April 2025, 3I Atlas had reached 4.2 AU from the Sun and was beginning its long inward journey toward perihelion, scheduled for August. The object was brightening slowly as it approached, becoming slightly easier to observe as the Sun-Earth object geometry improved. I had settled into a routine. Observe it every few nights when weather and telescope schedule permitted, update the orbital solution, check for any signs of activity or deviation. Most nights showed nothing unusual, just a faint point of light following its predicted path, rotating with its slowly changing period, showing no signs of the dramatic behavior that had characterized its December and February activity. It was almost boring, which was a relief. Boring meant predictable. Predictable meant I could catch up on other work, write overdue papers, advise students, attend to all the regular professional responsibilities I'd been neglecting. But I couldn't quite shake the feeling that I was watching something waiting, that 3I Atlas was dormant, not dead, that whatever had driven its behavior before was still there, still functioning, just operating on a timescale that made human patience seem frantic by comparison. In early May, that feeling proved justified. The deviation started subtly small positional discrepancies that appeared in the tracking data over the course of several nights. Once again, 3I Atlas was not quite where it was supposed to be according to the gravitational models. Once again, it was experiencing a non-gravitational acceleration. But this time, something was different. The acceleration wasn't directed along the velocity vector like before. It wasn't a braking maneuver or a course correction to a new orbit. This acceleration was directed inward, toward the Sun, perpendicular to the object's motion. It was changing its orbital inclination. Over the course of 3 weeks in May, 3I Atlas gently nudged itself onto a new trajectory that was more aligned with the plane of the inner solar system. The acceleration was small, precise, sustained exactly the kind of maneuver you'd make if you were trying to set up a close approach to a planet, specifically Earth. Let me be very clear about what close approach means in this context, because I don't want to sensationalize this or create panic where none is warranted. 3I Atlas is not going to hit Earth. Its new trajectory, as best we can calculate it, will bring it within approximately 0.7 AU of our planet in December 2025, about 105 million kilometers. Roughly 2/3 of the distance from Earth to the Sunday. That's far. That's millions of times farther than the Moon. That's farther than most asteroids classified as near-Earth objects ever come. But it's closer than the object would have been on its previous trajectory. And the timing is interesting. December 2025 puts the close approach at a point when Earth and 3I Atlas will be in the same general region of the solar system, with relatively favorable geometry for observation, for communication, for whatever you might want to do with an object that's deliberately maneuvered itself into your neighborhood. I ran the orbital calculations dozens of times, using different assumptions and different models. The conclusion was consistent. 3I Atlas had changed its trajectory specifically to arrange a moderately close pass by Earth in December. The professional discussions about this development were careful and measured, as always. JPL updated their orbital solution. The Minor Planet Center issued a revised ephemeris. Papers were submitted analyzing the acceleration vector and proposing mechanisms. But underneath the professional calm, I could sense a growing unease in the community. Because 3 separate course corrections, each precisely timed and directed to achieve a specific orbital outcome, were getting very hard to explain as random outgassing or asymmetric sublimation or any other natural process. The pattern was too clear. The targeting was too accurate. 3I Atlas was going somewhere specific, and it had chosen to come closer to us. June and July were quiet months, observationally. 3I Atlas continued on its new trajectory without further deviation, brightening slowly as it approached the inner solar system. By mid-July, it had reached magnitude 19, just barely visible in amateur telescopes with patient observers and dark skies. I spent those months doing something I hadn't done before, looking backward instead of forward. If 3I Atlas was artificial, if it was some kind of probe or remnant or artifact from another intelligence, then maybe there were clues in its journey before it reached us. I started tracking its trajectory backward, calculating where it had come from before entering our solar system. The math is straightforward but tedious. Take the object's current position and velocity, remove the gravitational influence of the sun and planets, integrate the equations of motion backward in time, and see where the trajectory leads. For most interstellar objects, this calculation gives you a rough direction but not a specific source, because the stellar motions over millions of years scramble the trajectory beyond recognition. You can say an object came from the general direction of Ophiuchus or Sagittarius, but you can't identify a particular star system without more information. But 3I Atlas had only been traveling for perhaps a few million years at most, based on the accumulated cosmic ray damage visible in its spectrum. Over that time scale, stellar motions are measurable but not overwhelming. If you knew the precise trajectory, you could backtrack it to a source region. I integrated the trajectory backward for 3 million years, accounting for the sun's motion through the galaxy, the local stellar drift, the gravitational influence of nearby stars. The calculation took several days of computing time, and the uncertainty grew exponentially as I went further back, but a pattern emerged. 3I Atlas appeared to have originated from a region of space approximately 180 light-years away in the constellation Ophiuchus. Not a specific star, the uncertainty was too large for that, but a region containing several dozen candidate stars, most of them K-type dwarfs or M-type red dwarfs, stars slightly smaller and cooler than our Sun. I cross-referenced that region with exoplanet catalogs, looking for any systems known to contain planets. 3 of the candidate stars had confirmed planetary systems discovered by the Kepler Space Telescope years earlier. Small planets, mostly super-Earths and mini-Neptunes, nothing obviously habitable by Earth standards, but planets nonetheless, orbiting in the right general direction. It proved nothing. Correlation without mechanism is just coincidence. But it gave me a target region, a possible origin, a story I could tell myself about where this strange object might have started its journey millions of years ago. And late at night, when I was tired enough to let my thoughts wander without scientific discipline, I imagined a civilization around one of those distant stars, launching probes into the galaxy, sending them out to explore neighboring systems, to observe, to report back, to serve whatever purpose their makers had intended. I imagined 3I Atlas leaving its origin system millions of years ago, before humans existed, before Homo sapiens had evolved, when our ancestors were small primates in African forests with no concept that the lights in the sky were distant suns with their own worlds. I imagined it traveling through the vast darkness between stars, patient and tireless, following a trajectory calculated to bring it through our solar system at a particular time, for a particular reason. And I wondered if it knew we were here now, if it could detect our radio transmissions and our satellites and our spacecraft scattered across the inner solar system, if it was aware that the system it had been sent to visit had become inhabited in the time since its journey began. I wondered if that awareness was why it had changed course. August arrived with the kind of heat that makes you grateful for air conditioning and night shifts. 3I Atlas reached perihelion on August 23rd at a distance of 1.79 AU from the Sun, passing between the orbits of Mars and Earth exactly as the revised trajectory had predicted. The object was at magnitude 17 now, bright enough that dozens of observatories were tracking it, collecting photometry and spectroscopy and astrometry, documenting its behavior with unprecedented detail. If something unusual happened, we'd catch it. If it flared again, if it accelerated, if it did anything anomalous, the data would be there. It did nothing. It sailed through perihelion with perfect gravitational propriety, following Kepler's laws, showing no signs of activity beyond the continuing slow evolution of its rotation period. The spectrum remained unchanged, dark, red, organic rich. The light curve showed complex variation, but nothing that suggested anything other than an irregularly shaped body tumbling through space. It was almost disappointing. After months of anticipation and speculation, 3I Atlas passed its closest approach to the Sun like any other asteroid, unremarkable and silent. But I kept watching, because perihelion wasn't the important point. December was. The Earth flyby, 0.7 AU, 4 months away. That was when the geometry would be optimal, when the object would be closest to us, when whatever it might do would be most likely to happen. So I waited, and I watched, and I collected data through late August and into September, as 3I Atlas swung past perihelion and began moving outward again, now on a trajectory that would bring it into Earth's general vicinity in 4 months. The rotation period had stabilized at 18.4 hours. The brightness was slowly fading as the object moved away from the Sun. Everything was calm, predictable, normal. And then, on September 18th, 2025, the signal pattern came back. It wasn't a brightness spike this time. It was something different, something that required radio telescopes to detect. A researcher at the Arecibo Observatory successor facility, a next-generation radar and radio telescope in Chile, had been conducting routine observations of 3I Atlas as part of a program to study the surfaces of unusual small bodies. The radar could reveal details about surface texture, rotation state, and gross shape that were impossible to determine from optical observations alone. The radar echo came back normal. A rough, irregular surface consistent with a rubble pile or fractured monolith, rotating with the expected 18.4-hour period. Nothing unusual in the structure or composition. But embedded in the radar return, at frequencies slightly offset from the transmitted signal, was something unexpected. A faint, periodic modulation. Not strong enough to be a reflection from a rotating surface feature, not at the right frequency for Doppler shift from rotation. Something else entirely. A signal component that shouldn't have been there. The Arecibo team documented it, analyzed it, and sent out a cautious note to the community. Possible coherent signal detected in radar observations of 3I Atlas. Natural explanation unclear. Request independent confirmation. I saw the note at 2 a.m. while scrolling through email in bed, unable to sleep. I sat up, read it 3 times, then went to my desk and pulled up the raw data files they'd attached. The modulation was subtle but real. A periodic variation in the radar return signal at a frequency of approximately 0.67 hertzes, one cycle every 1.5 seconds that persisted for the duration of the observation, roughly 40 minutes. 1.5 seconds. A very specific period. Nothing particularly special about it from a physics perspective, but short enough to be clearly artificial if it was intentional. Natural processes generally don't produce signals at that kind of timescale unless they're extremely energetic pulsar rotations, orbital frequencies of neutron star binaries, that kind of thing. And 3I Atlas was just a dark, cold rock 4 AU from the Sun. I spent the rest of the night analyzing the signal structure, looking for patterns in the modulation. It wasn't random noise, there was too much coherence in the phase. But it also wasn't obviously encoding information, at least not in any format I recognized. No binary pulses, no AM or FM modulation, no obvious carrier structure, just a simple, repeating waveform at 0.67 hertzes, embedded in the radar echo of an interstellar object that had already proven it could change course. By morning, 3 other observatories had confirmed the signal. By the end of the week, it was being studied by radio astronomers around the world. By the end of September, there were preprint papers proposing mechanisms ranging from plasma oscillations in the ionized gas around the object to coherent reflection from crystalline structures in the surface to deliberate transmission. That last option, deliberate transmission, was only mentioned in one paper, buried in the discussion section, hedged with so many qualifiers and caveats that it was almost invisible. But it was there, in print, in a peer-reviewed journal. The possibility that 3I Atlas was transmitting a signal. Nobody wanted to say the word artificial outright. Nobody wanted to be the first to make that claim publicly. But the conversation was shifting, slowly, from what natural process could explain this, to if this were artificial, what would that mean? October was chaos, professionally and personally. The media discovered the radar signal, and the story exploded in a way that the orbital anomalies never had. Headlines appeared: Interstellar object sending signals. Is 3I Atlas trying to communicate? Scientists detect radio transmissions from mysterious space rock. Most of the coverage was inaccurate or sensationalized. Some was thoughtful and well-researched. All of it created pressure on the astronomical community to either confirm or deny the artificial origin hypothesis, pressure that science isn't designed to handle, because science works on evidence and replication and consensus, not on headlines and deadlines and yes or no answers. I gave exactly one interview to a science journalist I trusted who agreed to let me review the article before publication. I was careful, measured, professional. I said the signal was real but unexplained. I said natural mechanisms hadn't been ruled out. I said we needed more data before drawing conclusions. And then, off the record, I told her, but if you put a gun to my head and made me bet on natural versus artificial, I'd bet on artificial. The pattern is too clear. The behavior is too consistent. 3 course corrections, periodic flares, now a radio signal. Each piece alone might be natural, but all of them together? That's not how nature works. Nature is messy. This is neat. She kept that off the record, as promised. But I saw her face when I said it, the way her expression shifted from journalist collecting quotes to human confronting implications. Because if 3I Atlas was artificial, if it was some kind of probe or messenger or artifact from another intelligence, then everything changed. Our place in the universe, our understanding of how common life and technology might be, our expectations for what we might find out there in the dark, all of it would need to be revised. And more immediately, more practically. If it was artificial and it was heading toward Earth, then we needed to think about what that meant, what it wanted, what we should do about it. Those were questions I wasn't qualified to answer. Nobody was. We'd spent decades preparing for the possibility of detecting radio signals from distant civilizations, building protocols and response strategies and international frameworks for how to handle first contact with extraterrestrial intelligence. But all of those protocols assumed the signal would come from light years away, from a civilization we could never physically reach, from a transmission that was essentially informational photons carrying a message across the void. Nobody had really prepared for the scenario where the first contact wasn't a message but a visitor, where the signal came from something already inside our solar system, moving, maneuvering, approaching. 3I Atlas wasn't just announcing itself, it was coming here. November brought the first direct imaging of 3I Atlas's shape, courtesy of the James Webb Space Telescope. JWST's near-infrared instruments could just barely resolve the object as something more than a point source, revealing a blurry, elongated blob that looked roughly cylindrical, with irregular protrusions at both ends. The shape analysis suggested an object approximately 800 meters long and 200 meters in diameter, larger than the earlier estimates, more elongated than most asteroids, but not impossibly so. Plenty of natural asteroids are elongated. Plenty have irregular shapes from impacts and gravitational encounters and the chaotic processes of formation. But combined with everything else, the shape added to the pattern. Elongated objects are efficient for interstellar travel. They have high strength-to-mass ratios. They can rotate for stability. They present a small cross-section to interstellar dust and radiation. If you were designing a probe to travel between stars, you might build it that way. Of course, if you were a cosmic process breaking up a comet nucleus or collisionally grinding asteroids into fragments, you might produce that shape too. Elongation proves nothing, except it fit. Everything about 3I Atlas fit the profile of an artificial object just well enough that you couldn't dismiss the possibility, but not quite cleanly enough that you could prove it definitively. It was Schrödinger's artifact, simultaneously natural and artificial until some final observation collapsed the wave function and forced us to choose one interpretation or the other. By late November, with the December close approach just weeks away, the object was bright enough magnitude 13 that serious amateur astronomers with 8-inch or larger telescopes could photograph it. Images started appearing online, shared by backyard observers around the world. A faint, elongated smudge against the background stars, moving slowly night by night, heading in Earth's direction. The public awareness grew. Not universal, most people were still unaware that an interstellar object was approaching, but significant enough that it had penetrated mainstream consciousness. Late-night comedy shows made jokes about alien visitors. News websites ran explainer articles. Social media was a mix of excitement, skepticism, and anxiety. And through it all, 3I Atlas continued its steady approach, following the trajectory it had set for itself back in May, heading toward a point in space that Earth would occupy in mid-December, 23 days from now. I watched it every clear night, tracking its position, measuring its brightness, looking for any sign that it might do something unexpected before the close approach. The signal continued, that 0.67 Hz modulation, steady and unchanging, visible to any radio telescope that cared to look. The rotation period was now 18.9 hours, still slowly increasing. Everything else was quiet. It felt like the calm before something, though I couldn't say what. December arrived cold and clear. The observatory was busy with multiple research programs, but I'd blocked out time around the predicted close approach date, December 14th, to ensure I could observe whatever might happen. 3I Atlas would pass closest to Earth at approximately 1630 UTC, when it would be 0.71 AU away, about 106 million kilometers, 2/3 of the distance to the Sun. The geometry was favorable for Northern Hemisphere observers, with the object visible in the evening sky after sunset, passing through the constellation Taurus near the Pleiades star cluster. In the week leading up to closest approach, the object brightened to magnitude 11, just below naked eye visibility, but easy in binoculars. For the first time, non-specialists could see it for themselves, not just trust data plots in scientific papers, but actually look up and see the faint point of light that had traveled from another star system and maneuvered itself into our neighborhood. I gave a public talk at the observatory on December 10th, 4 days before closest approach. About 200 people showed up, filling the auditorium beyond capacity, standing in the aisles and sitting on the floor. They had questions. Lots of questions. Is it alien? I don't know. Is it dangerous? Probably not. It's small, it's far away, and it hasn't shown any hostile behavior. But we don't really know what it is or what it's doing, so we can't rule anything out. What happens on December 14th? It passes by at its minimum distance and then continues outward. Whether anything special happens at that moment, we'll have to wait and see. Are we sending any messages to it? Not officially. There's been discussion at various governmental levels about protocols for communication, but no consensus has been reached. The scientific community has been observing it passively, collecting data, but not transmitting anything deliberately. Should we be trying to communicate? That's above my pay grade. That's a question for philosophers and ethicists and international policymakers. I'm just trying to understand what it is and what it's doing. But do you think it's intelligent? Do you think it's watching us? I paused after that question, looking out at the audience, seeing the mixture of excitement and apprehension in their faces, the human need to know what's out there in the dark and whether we're alone. I don't know, I told them honestly, but I think we're going to find out soon. December 13th was the longest night of my life, though nothing dramatic happened. Just the anticipation, the weight of waiting, the knowledge that something was about to occur but not knowing what. I was at the observatory by sunset, running system checks, calibrating instruments, setting up the observation sequence. Other staff and students drifted in and out, everyone finding excuses to stop by and check on the preparations. The atmosphere was tense, excited, uncertain, like waiting for a storm that might or might not arrive. Elena had flown in from Europe to observe with me. We'd been collaborating closely since those early conversations about the brightness spikes, and she'd become something like a colleague friend, the kind of person you trust, with half-formed thoughts and wild speculations, because you know they'll take them seriously, without judging. We set up in the control room, surrounded by monitors showing telescope status, weather conditions, sky images, data streams. The plan was simple. Track 3I Atlas continuously through the night, taking optical photometry, spectroscopy, and coordinating with radio observations from other facilities. Document whatever happened during the closest approach window. The object rose in the eastern sky around 6 p.m. local time, already visible as a magnitude 11-point source moving slowly against the stars. We started the observation sequence: image, measure, record, repeat, building a light curve in real time, watching for any change in brightness or behavior. For the first few hours, nothing unusual happened. 3I Atlas followed its expected path, rotating with its 18.9-hour period, reflecting sunlight with its characteristic dark red spectrum. The radio signal continued at 0.67 hertzes, unchanged from what it had been for the past 3 months. Midnight passed. The object was high in the southern sky now, in the gap between Taurus and Orion, moving against the background stars fast enough that you could see the motion if you compared images taken an hour apart. Elena and I took turns at the monitors, one of us watching the data streams while the other tried to rest on the couch in the corner. Neither of us actually slept. We just lay there with our eyes closed, listening to the subtle sounds of the observatory, the hum of cooling fans, the occasional clunk of the telescope mount tracking, the quiet beeps of incoming data, and waiting. At 3:47 UTC on December 14th, 11 hours before closest approach, the data refreshed with new orbital parameters. And I saw that 3I Atlas had changed course again. The acceleration was small, subtle, almost imperceptible if you weren't looking for it, but it was there in the residuals, in the difference between where the object actually was and where the gravitational models said it should be. 3I Atlas was accelerating again, and this time the vector was pointed directly toward Earth. Not on a collision course, the change was far too small for that, just a few centimeters per second of velocity change, but enough to slightly modify the geometry of closest approach. Enough to reduce the minimum distance from 0.71 AU to approximately 0.68 AU. Enough to be deliberate. I stared at the numbers on the screen, double-checking my calculations, running the orbit integration forward to see what this change meant. The new trajectory was cleaner, more precise, as if 3I Atlas was fine-tuning its approach to hit an exact target point in space and time. "Elena," I said quietly, "it's happening again." She came over to look at the monitor, leaning over my shoulder to read the orbital elements. I heard her breath catch. "It's targeting us," she said. Not a question, a statement. Or targeting a specific position relative to us. Some optimal geometry for whatever it's planning to do. When does it finish the maneuver? I checked the acceleration vector and its apparent magnitude. If it continues at this rate, probably within a few hours, well before closest approach. We sat in silence for a moment, watching new data points accumulate on the position plot, each one confirming that 3I Atlas was exactly where the modified trajectory predicted. "We should notify people," Elena said. "JPL, ESA, the coordination centers. They need to know this is happening." I nodded and started drafting emails, trying to keep my language clinical and precise, even though my hands were shaking slightly on the keyboard. Updated orbital solution shows additional non-gravitational acceleration beginning approximately 3:45 UTC. Object appears to be making final trajectory adjustment to modify closest approach geometry. Projected minimum distance now 0.68 AU. Acceleration magnitude approximately 2 centimeters per second. 2 vector directed toward Earth position at closest approach time. I hit send and watched the email disappear into the network, carrying the news to dozens of observatories and coordination centers and governmental agencies that had been watching 3I Atlas for months. And then we went back to observing, because that was all we could do. Watch, measure, record, and wait to see what happened when an interstellar object completed its final approach adjustment and arrived at the position it had been maneuvering towards since May. The acceleration continued until approximately 7:20 UTC, at which point it ceased as abruptly as it had begun. 3I Atlas was now on a trajectory that would bring it to within 0.677 AU of Earth at exactly 1633 UTC, 3 minutes later than the previous prediction and 3 million kilometers closer. The precision was striking. Whatever was controlling the object's trajectory had calculated the required maneuver to within seconds of timing and thousands of kilometers of position. That level of accuracy required real-time navigation, constant position updates, active guidance. It was the kind of precision you'd get from a spacecraft with thrusters and a navigation computer, not from a dark rock passively following Newtonian mechanics. By mid-morning, the news had spread through the astronomical community and beyond. The observation programs intensified. Every available telescope was pointed at 3I Atlas, collecting data at the highest possible cadence. Radio observatories around the world were tracking the 0.67 Hz signal. Radar facilities were pinging the object, measuring its rotation state and surface properties. Space agencies were repositing satellites to get better viewing angles. Everyone was watching, waiting for 1633 UTC. I tried to eat breakfast around 9 a.m. and couldn't. My stomach was tight with a mixture of excitement and apprehension that felt almost like fear but sharper, more electric. This was it. This was the moment everything had been building toward since that first trajectory change in March 2024, 20 months ago. 3I Atlas had come from another star system. It had changed course 3 times to arrange this specific encounter. It had been transmitting a signal for months, and now, in 7 hours, it would reach the point in space it had been navigating toward. What happened then would either confirm that it was just a very unusual but ultimately natural object following complex but explicable physics, or it would confirm that we were not alone, that intelligence existed beyond Earth, and that it had sent something across the light years to visit us. The day passed in a blur of observations and data analysis and mounting tension. By noon, 3I Atlas was magnitude 10, visible in good binoculars, well placed in the afternoon sky for observers in the Americas. By 3 p.m., it was magnitude 9, and you could see it in small telescopes as a distinct, elongated smudge. The radio signal remained constant at 0.67 Hz. The rotation period was still 18.9 hours. The spectrum was unchanged. Everything was quiet, normal, predictable except for the knowledge that this object had deliberately positioned itself for this moment. At 4 p.m., I stepped outside the observatory dome to look at the sky. It was clear, cold, the sun low in the west, stars beginning to emerge in the deep blue of early evening. I couldn't see 3I Atlas with my naked eyes, but I knew where it was just above the eastern horizon, in Taurus, moving toward us at 15 kilometers per second. Elena joined me, bringing coffee that neither of us drank. "What do you think is going to happen?" she asked. I shook my head. I have no idea. Maybe nothing. Maybe it just passes by and continues outward, and we spend the next decade arguing about whether it was natural or artificial. Maybe it does something. Yeah, maybe it does something. We stood in silence, watching the sky darken, waiting for the universe to reveal whatever truth it had been hiding in the trajectory of this strange visitor from between the stars. At 4:30 p.m., we went back inside. 1 hour and 3 minutes until closest approach. The final hour was almost unbearable in its slowness. Every minute felt stretched, extended, as if time itself was dilating in anticipation of what might come. We watched the monitors. Data streamed in from observatories around the world, everyone seeing the same thing. 3 I-Atlas approaching the designated point, following its trajectory with perfect precision, showing no signs of new activity. At 16 UTC, 33 minutes before closest approach, the radio signal changed. Not dramatically, not suddenly, but measurably, clearly. The 0.67 Hz modulation increased in amplitude by approximately 40%, becoming stronger, more prominent against the background noise. Observatories around the world confirmed it simultaneously. The signal was intensifying as the object approached. "It's turning up the volume," Elena said, her voice tight. "Like it wants to make sure we're paying attention." At 16:15 UTC, 18 minutes before closest approach, the optical brightness began to increase. Not a sudden flare like the February event, but a gradual, steady, brightening 0.1 magnitudes per minute, smooth and controlled. I watched the light curve plot climb, the data points marching upward with mechanical regularity. This wasn't outgassing or impact events or any random process. This was something turning on, activating, powering up. At 16:25 UTC, 8 minutes before closest approach, 3 I-Atlas had brightened by nearly 1 full magnitude, and the radio signal had doubled in strength. And then, at 16:28 UTC, 5 minutes before closest approach, something new appeared in the spectrum. A narrow emission line at 589.3 nanometers, sodium. The same wavelength as the sodium D line that appears in Earth's atmosphere, in certain types of stars, in gas clouds in space. But this line wasn't there before. It appeared suddenly, cleanly, as if someone had switched on a sodium lamp somewhere on or inside the object. "That's not natural," I said aloud, to Elena, to myself, to anyone listening. "That's not how asteroids behave." She was already on the phone with other observatories, confirming the detection. "Multiple facilities seeing the same emission line. It's real. Something is glowing on that object." 16:30 UTC. 3 minutes to closest approach. The brightness was still increasing. The radio signal was still strengthening. The sodium emission line was growing brighter. I pulled up the real-time trajectory plot, showing 3 I-Atlas's position relative to Earth. The object was approaching the closest approach point along a curve that looked computer-generated in its smoothness. 16:32 UTC, 1 minute. The observation room was silent, except for the hum of electronics and the soft clicks of data being recorded. I was aware of my heartbeat, too fast, too loud in my ears. 16:33 UTC, closest approach. And 3 I-Atlas flared. It wasn't like the February flare. It wasn't a brief spike and fade. This was sustained, controlled, a steady emission of light that brought the object to magnitude 5 naked eye visibility, easily visible from any dark sight, a new point of light in the evening sky that hadn't been there minutes before. The radio signal peaked at the same moment, the 0.67 Hz modulation now strong enough to be detected by amateur equipment. The sodium emission line became brilliant, dominating the spectrum, as if the entire object was glowing with the yellow light characteristic of sodium vapor. And then, underneath it all, in the radar returns, and the high-resolution spectra, and the precisely timed photometry, we detected something else. Structure. The brightness increase wasn't uniform across the object. It was coming from specific locations on the surface, 3 distinct bright spots arranged in a triangular pattern, each one pulsing in synchronization with the 0.67 Hz radio signal. 3 lights, blinking, in perfect time. I felt something shift in my chest, some fundamental assumption about the nature of reality quietly rearranging itself, because that pattern wasn't random, it wasn't natural. It was geometric, regular, communicative. It was intentional. Elena's hand found my shoulder, gripping tight. Neither of us spoke. We just watched the data stream in, watched the evidence accumulate that something artificial was out there, 106 million kilometers away, deliberately signaling us at the moment of closest approach. The flare lasted for exactly 18 minutes, the same duration as the February event. And then, at 16:51 UTC, the lights began to fade. The brightness decreased smoothly, the radio signal weakened, the sodium emission line dimmed. By 17 UTC, 3I Atlas had returned to its baseline state magnitude 9, faint radio emission, featureless spectrum. The object continued past Earth on its trajectory, moving outward toward the orbit of Mars and beyond, beginning its long journey away from the inner solar system. It had done what it came to do. It had shown us what it was, and now it was leaving. The aftermath was chaos, in the professional sense. Emergency conferences, hastily organized panels, governmental briefings, international coordination meetings. Everyone wanting data, wanting explanations, wanting to know what this meant and what should be done about it. The evidence was incontrovertible now. You could argue about interpretation, about what exactly 3I Atlas was and where it came from and what its purpose might be, but you couldn't argue that it was natural. Not after the December 14th event. Not after 3 synchronized lights pulsing in perfect time. Not after a controlled flare at the exact moment of closest approach. Not after months of precision navigation that brought it to that specific point in space at that specific time. 3I Atlas was artificial. It was technology. It was proof that intelligence existed beyond Earth, and that it had reached out across the interstellar void to visit us. The public reaction was complicated. Some excitement, some fear, a lot of confusion and uncertainty about what this meant for humanity's place in the universe, but also a strange sense of vindication, as if we'd always known we weren't alone and now we finally had proof. The scientific community was already deep into analysis mode, trying to understand every aspect of what we'd observed. Papers were being written at a frantic pace. Data was being shared across international boundaries with unprecedented cooperation. The question had shifted from, is it artificial, to, what can we learn from it? Because 3I Atlas wasn't just proof of alien technology. It was a sample. A messenger, a data point in the larger question of how common intelligence might be in the galaxy and what form it takes when it develops. And it was still here, still in our solar system, still potentially observable as it receded outward. In the weeks after closest approach, I continued tracking the object as it moved away from Earth. The brightness faded as the distance increased, dropping below magnitude 10 by late December, magnitude 12 by mid-January. The rotation period continued its slow increase, now approaching 20 hours. The radio signal persisted, steady, at 0.67 hertzes, detectable by large radio telescopes but gradually weakening as 3I Atlas receded. Several facilities were committed to tracking it as long as possible, documenting its behavior, watching for any new course changes or unexpected activity, because the big question now wasn't whether 3I Atlas was artificial. The big question was, what happens next? Is it leaving the solar system permanently? Its mission complete? Whatever data it collected now being stored or transmitted back to its origin across centuries of light speed delay? Or will it do something else? Will it maneuver again? Will it visit another planet? Examine another part of our system? Deploy something we haven't detected yet? And the even bigger question, the one that kept me awake at night, are there others? If one civilization sent a probe to our solar system, arriving just as we develop the technology to detect and track it, how likely is it that they're alone? How many other probes might be out there, traveling between stars, visiting systems, observing and reporting back? How many might have passed through our system before we had telescopes to see them? How many might arrive in the future? The universe suddenly felt more populated, more active, more alive, with the possibility of intelligence and curiosity and exploration, and also more uncertain. because we'd had our first confirmed contact with alien technology and we still didn't know what it wanted or why it had come or what message it might have been trying to convey with those 3 blinking lights. It's now late February 2026. I'm writing this in my office at the observatory, looking at the latest position data for 3I Atlas on my screen. The object is at 5.2 AU now, roughly the distance of Jupiter's orbit, magnitude 15 and fading. The trajectory has stabilized, no more course corrections, no more accelerations. It appears to be following a standard elliptical orbit now, with a period of approximately 14.8 years and an aphelion at 35 AU well beyond Neptune, deep in the Kuiper Belt region. If that orbit holds, 3I Atlas will return to the inner solar system in 2040. 14 years from now, it will swing back around, pass through perihelion again, perhaps make another close approach to Earth. I'll be retired by then, probably. Or at least older, slower, hopefully wiser. But I'll be watching, if I can, because I need to know if it comes back. I need to know what happens in that second pass, whether it behaves differently, whether it tries to communicate again, whether we've learned enough about it in the intervening years to understand what it is and what it wants. For now, though, I'm left with data and memories and questions. I'm left with the knowledge that we detected an interstellar object that exhibited impossible behavior, that changed course multiple times, that positioned itself for a deliberate encounter with Earth, and that signaled us at the moment of closest approach with unmistakable artificial light. I'm left with the understanding that we are not alone, that someone or something out there has the technology to send probes between stars, and that at least one of those probes visited us. I'm left wondering if they're disappointed that we couldn't understand their message, or satisfied that we at least noticed they were here, or completely indifferent to our existence, because we're just one more planetary system among billions, and they've seen it all before. I'm left with the memory of standing outside the observatory on December 14th, looking up at the sky just after closest approach, seeing 3I Atlas with my naked eyes as a faint yellow point of light in Taurus, and feeling the weight of cosmic time and distance settle onto my shoulders like a physical thing. We are small. We are young. We are alone on our pale blue dot in ways that we weren't before, now that we know for certain that others exist. But we are also part of something larger, a universe that contains intelligence, curiosity, exploration, communication across the vast dark between stars. 3I Atlas came from somewhere else. It maneuvered to visit us. It showed us what it was. And now it's receding back into the deep, carrying its secrets with it, leaving us to wonder and watch and wait for what comes next. The data is still coming in. The observations continue. The analysis proceeds at its steady, methodical pace. And somewhere out there, 5.2 AU away and growing more distant every day, a dark, elongated object tumbles slowly through space, following an elliptical path that will bring it back to us in 14 years, while a faint radio signal pulses at 0.67 hertzes into the cosmic background, saying something we don't yet understand to anyone who cares to listen. I care to listen. I'll keep listening as long as I can, watching that faint point of light recede into the dark, tracking its position, updating the orbital models, looking for any sign that it might surprise us again. Because if 3I Atlas taught us anything, it's that the universe is stranger and more purposeful than we assumed. That motion can be intentional at cosmic scales. That we are being observed, visited, perhaps even evaluated by intelligences that mastered interstellar travel while we were still learning to make fire. And that the question we should be asking isn't, are we alone? We have the answer to that now. The question is, what do they want? And what happens when they come back? I'm watching the latest data refresh on my screen. It's 3:47 UTC, again the same time I saw the first major trajectory change back in December 2024, 15 months ago. The timing is probably coincidence, but I've stopped believing in coincidence where 3I Atlas is concerned. The new orbital parameters show what I expected. Stable, elliptical orbit, no deviation, continuing outward. Still 14.8 years until perihelion return. Still fading into the dark. But there's something new in the latest observation report from Arecibo. A note flagged for my attention. Possible brief acceleration event detected at approximately 2:15 UTC. Magnitude uncertain. Request confirmation from other facilities. I feel my heart rate pick up, that familiar electric tension returning. I pull up the raw tracking data, compare it to the predicted ephemeris. There's a small residual, just a few arcseconds, barely significant. Could be measurement error, could be random noise in the tracking data. Or it could be the beginning of another maneuver. I check the latest radio observations. The 0.67 Hz signal is still there, unchanged in frequency, but possibly slightly stronger than it was yesterday. I run a quick orbital integration, projecting forward to see what a small acceleration at 2:15 UTC might mean for the future trajectory. The solution takes a moment to compute, and when I see the result, I sit very still in the dark office, lit only by monitor glow, and realize that if this acceleration is real, if the measurement is accurate, then 3I Atlas is making another course correction. A small one, subtle, but directed in a way that will modify its aphelion, change its orbital period, alter where it will be in 14 years when it returns to the inner solar system. The new trajectory, if this holds, won't bring it back in 2040. It will bring it back sooner, much sooner. The projected perihelion return date has shifted forward to late 2026, 9 months from now, and the minimum Earth approach distance at that perihelion pass is calculated at 0.23 AU. Closer than Venus, closer than Mercury, 3 times closer than the December 2025 flyby. I stare at the numbers, checking and rechecking my calculations, looking for errors or misunderstandings, but the math is clear. If 3I Atlas has begun accelerating again, if it's modifying its orbit to return sooner and approach closer, then whatever it did in December was just the beginning. It's coming back, and this time, it will come much closer. I reach for the phone to call Elena, to alert the tracking networks, to sound the alarm that our visitor from between the stars has changed course again. But before I dial, I pause and look out my window at the pre-dawn sky, where the stars are just beginning to fade as morning approaches. Somewhere out there, invisible to my eyes but present in the tracking data, 3I Atlas is turning, accelerating, modifying its trajectory with precision and purpose. Coming back to us, coming home. Stay curious, stay awake, and welcome back to Sleepy Cosmos.